Hi everyone, and welcome to this video for P8105, a course on data science. This is intended as the first video in the series, and in it I'm going to try to provide a working definition of data science. From there, I'm going to see how that definition guides the ways that I prefer to do data science and data scientific work. This is more about a thought process than about working examples, but it does provide useful context for later videos in which we're actually going to see some coding in action. And with that, I'm going to go ahead and jump in. So, what is data science? I think that's a good question for a variety of reasons, and foremost among those is that data science is still a pretty new area. What I mean by that, and this is a figure from Google Trends, is that nobody was really thinking about data science or searching for data science up until relatively recent history. This shows from 2004 up through roughly 2019, and you can see up until 2012, 2013, give or take, this was not really on anybody's mind, and then from there it has grown to become very, very popular. I'd say exceptionally prevalent, both in academic circles and outside of academia. People are really interested in what data science is. And especially in the early part of that, I would say, through 2014, 15, 16, there were a variety of folks who were reacting to the emergence of data science by proposing what I would consider some not great definitions. And among these were things like data science is just statistics or computer science or machine learning. The data science is essentially a rebranding of an existing skill set. Others thought that it was sort of the mashup of each of these different things. Some people thought that data scientists were people who worked exclusively with big data. Nate Silver weighed in, data scientist is just a sexier word for a statistician. Some thought that computer scientists or the data scientists were better at computer science than statisticians, and the reverse, right? Hadley Wickham, I think this was largely tongue-in-cheek, but he weighed in, at least at a conference where I saw a presentation, that a data scientist is a statistician who is useful. And as at least a biostatistician, I gotta say that both hurt and in some ways felt like a reasonable reaction. But also, there's this idea that a data scientist is a good statistical analyst, or a data scientist or is a statistician who knows how to code in Python. And like I say, these are all definitions that I don't think are particularly great, but that were kicked around, especially in the years immediately after the emergence of data science, but before there was any real consensus about it. Right. So, one of the things that you can't avoid, I think, if you start trying to define data science is this Venn diagram produced by Drew Conway, I think somewhere in the neighborhood of 2014. And the idea here is that there are three overlapping bubbles. One of them is math and statistics, and one of them is hacking skills, and one of them is substantive expertise, and you get sort of various intersections of these things to give you either machine learning or a danger zone or traditional research. But if you've got some of all three of those, then you're sort of there in data science. And my understanding is that here, hacking skills is loosely thought of as things like something like computer science, but as much as anything, the ability to cobble together code, the ability and the willingness to write code that does the thing that you want it to do, whether that's because you have a really solid understanding of how to write code from scratch, or because you're able to spend some time on Stack Overflow finding the skill sets, the answers that you need to do the thing that you want. And this, like I say, this is sort of an early picture and is useful as far as it goes. One of the things that it did was encouraged other people to make figures, which I think got worse, not better. So this is data scientist here in the middle, and we've got 5 bubbles instead of 3, and then also like some tape holding things together. This wasn't so great. And then there's this one, which came out a couple of years later and sort of describes a modern data scientist, which is always kind of funny in the sense that kind of by definition, all data scientists are sort of modern. Like, you can't find a data scientist from back in the day. Anyways, so they list here things that you need to know in math and statistics and programming a database and domain knowledge and soft skills and communication and visualization. And there's like a list of things underneath each of those. And these, I think are sort of responding to a general consensus about what kinds of things are descriptive or what things might a data scientist do. And again, they're sort of useful as far as they go, but they're not great. And one of the reasons in particular that I think they're not great is because they took this extra step of showing what a data scientist might look like. And the way that they chose to depict data scientists are sort of like people who might have gentrified Brooklyn and then complained about the lack of diversity. And I just don't think that is ever a great way to depict what a data scientist is. And now, right now, in the time that I'm filming this video in the summer of 2020, I think it's particularly unfortunate that this was a visualization that they chose to go with. And what I want to draw your attention to is not just that this definition of data scientist is bad, but also that I think this representation of what a data scientist might be is just fundamentally flawed. It's just inaccurate. And anybody who wants to be can be a great data scientist. And so if this doesn't strike you as something that is particularly relevant to your own experience, don't let that disturb you. Don't let that bother you, put you off from becoming a data scientist. This is a flaw in this graphic, not in anything else. So it's, I hope, clear at this point that I think these definitions of data science are bad, but I want to be very explicit about why I think these are bad. And so there are sort of two things I'm going to start out with. First is that if data science is just something, then you sort of missed the point, right? The data science emerged in response to something, and if it was just a rebranding of an existing discipline, well, we wouldn't really need a new term. We would just all have switched over to become computer scientists or machine learners or statisticians or whatever it is. So the fact that data science exists means that there is something that is different from what had been done in the past. A data scientist is a good or a useful or whatever other kind of definition is, other than sort of being like a bit of a joke, these aren't really helpful in the sense that they're kind of deliberately judgmental, and they also depend on who is forming that opinion, right? That one person might say that a good statistician does this, and another person might say that a useless statistician does that. And if they're not in agreement, well, then you don't really have a definition. You've just sort of got opinions. The other thing that I want to point out is that almost certainly in every discipline, there are people who are doing data science and there are people who are not doing data science. And you can be good at statistics and not really want to do data science. And that's, I think, completely reasonable. So narrowing things down to say that a data scientist is a good this or a good that, I find sort of unfortunate as a framing. The other reason that these are bad is because the graphics that include like long list of skills, right? If you're going to do data science, then you need to be fluent in R and Python, and you need to know how to use MapReduce, and you better TensorFlow some things, and also be an excellent communicator, and don't forget about your domain knowledge in the business sense and all of this, right? Like, it's just unreasonable to expect that any one person is going to have that entire collection of skill sets, that there's some unicorn out there that can do everything. It's unrealistic and can be off-putting. It is entirely possible to be a data scientist without being able to do that entirely long collection of skills. And in some of those previous figures, I look at them and I think like, well, you know, I've got 20 to 25% of those skills on a good day. I still kind of think I'm doing all right as a data scientist. And so I think seeing just a long list of things and saying, well, I can't do all of them, so I'm not a data scientist, again, it's sort of off-putting in a way that's unnecessary. But it's not as if these definitions are just completely invaluable. It's not like they are completely wrong. There's a parable that is not as popular as I originally thought it was, but the idea is that if you took a bunch of scientists and blindfolded them, and you tried to put them next to an elephant, and you said, like, all right, describe what's going on with this elephant, and each of them sort of touched one part of the elephant and said, all right, well, I'm grabbing the tusk, so I think this is a spear, or it's a wall, or a rope, or you see a snake, whatever, that each of those is giving some sense of the local thing that they're able to get in contact with. And in the same way, data science is sort of like a big thing, and individuals might have their own experience of it, but you can sort of get at useful properties of something without defining what that something is. And it's also not really fair to just stack all of those things up and then say it's clear what it is, right? Like the descriptions that these blind folks, you know, reaching out and touching an elephant, they're not going to come up with some definition that describes what an elephant is any more than the people who are describing a very local structure about data science are going to be able to tell you what data science is either. But each of those things does give you, I think, some sense of what's important in the data science community, and that is something like using data in a principled way and trying to code effectively and try to code clearly. There's another thing that I actually like about all of the definitions that we've seen up to this point, and that's that data science is very clearly an interdisciplinary domain, that to do data science, you do have to have some collection of skills. You also need to be willing and able to engage with others who have expertise in an area that you're interested in, that you are not on your own going to be able to solve the problems in some area, no matter how much you know the data processing pipeline, or no matter how well you are able to implement some algorithm, unless you are able to communicate effectively and engage in a way that is both curious and critical, then you're not actually going to be able to have an impact in the domain that you thought you were going to. So all of that is sort of, I still haven't defined what I think data science is, and all of that is sort of a thought of when data science emerged and what kinds of things were happening. But I want to talk a little bit about why I think data science actually emerged to the degree that it has. And this is sort of leading up in the area, like up to about 2012, is that in that time period, people were very much thinking about what big data is and the emergence of big data. And there was a growing trend on prediction as an outcome that you might be interested in, prediction as a goal in itself, to be able to do, in one context, maybe precision health, in another context, to be able to sort of figure out exactly what somebody was maybe going to buy if you're going to be in a company, to do targeted advertising in some of these areas. Prediction became something in and of itself that was important. In science, at least, there was a lot of chatter about the reproducibility crisis. And what that means generally is that folks would try to replicate a study. Folks would try to understand whether or not the top-line results of a study were valid. And sometimes they were and sometimes they weren't. And while that is a much broader debate, it sort of got distilled into the idea about reproducibility as an important goal. Reproducibility meaning that somebody can, given the same data and same code, reproduce the same results. That became a real point of concern in the scientific community. And then I've emphasized that data science is interdisciplinary, and for some years up until then, there had sort of been a trend, especially in academia and in other areas, to move in a direction of things becoming more interdisciplinary. And so it's not as if any of those trends were new, they didn't exist without data science. They all existed, and they were important and remain important in their own right, but the sort of convergence of each of those into a broad umbrella of something called data science at least contributed to the perspective of that emerging field, that some of the things that mattered in data science was to be able to understand, in addition to traditional statistics and things like this, to know how to do big data, to understand what prediction is, to be proficient enough in coding to ensure that reproducibility was possible, and then to communicate effectively in an interdisciplinary way. So this is maybe a working definition more than anything else, but this is going to be, for the purpose of this class, the definition that we're going to use. And it's that data science is the study of formulating and rigorously answering questions using a data-centric process that emphasizes clarity, reproducibility, and effective communication. There's a lot of stuff that is sort of baked into that definition, including how you formulate questions, what does it mean to gather data, what does it mean to clean and analyze those data, what are the tools that you might use for answering questions rigorously rather than in sort of an ad hoc way. There's a lot there that is not exactly what we are going to focus on. So in this video collection of videos, what we're mostly going to focus on is the process, not so much the analytic approach, not so much the formulation of questions or the collection of data. What we want to know is, given some data, what are the best principles that you can use to ensure that you are analyzing data in a way that is clear and transparent and that other people can follow through on, and that you're doing all of this in a reproducible way and can disseminate your results publicly. And I guess sort of the caveat there is, I really strongly encourage you to get some training to understand how you should be answering questions in a way that's rigorous, right? To not just sort of punt on understanding what methods are and how you interpret the results of those things. You really do need to study that as well. It's just not the purpose that we're going to go after. I like this sort of a data science analogy, and this isn't one that I came up with, but for the life of me, I can't remember where I heard it first. And the analogy that I like for data science is something like the following: is if you go back to the beginning of the 1900s, two things were happening in transportation sort of simultaneously. In 1903, the Wright brothers had their first flight, and in 1908, the Model T rolled off the assembly line. And in the context of transportation, one of those was a really exceptionally groundbreaking achievement that applied to a very, very narrow collection of people. It was sort of the Wright brothers could fly and really nobody else could. And that's hugely important for transportation. It sort of points in a direction of the future, but it's very limited in who it's applicable to. The Model T is a similar advancement in the sense that it formalized it, it created a mechanism through which a very broadly and reasonably well understood technology, the automobile, was going to be available in a way that was much wider than it had been previously. And so the advent of the Model T, the development of a car that could be rolled off an assembly line, was a huge advance in transportation, but different from a first flight. It was different in the sense that this was focused on making sure that everybody had access to a very common technology. And so in data science, I worry that very often folks focus on the flying part and not the driving part. And that is, in data science, everybody gets really excited about artificial intelligence and deep neural nets, but a lot of what drives innovation, a lot of what drives success, a lot of what people really use is something like ggplot, right? Like, how are you going to organize your data and how are you going to make plots, right? Neural nets are great, they're interesting, they're fantastic, but the tidyverse is probably having more of an impact right now than AI is, or at least maybe. Depends on how you define impact. I'm going to return to that in a couple of minutes, but first I want to spend a few minutes talking about how you should learn data science. And what I encourage you to do in the context of learning data science is to try to learn, right? And I know that sounds kind of silly to say, but what I mean by that is, if you are getting started in this, you should not in any way be embarrassed by the fact that you are learning these things. You should talk to people, you should ask questions, you should get help, you should find online resources. And in doing all of those things, you should be trying to develop with the goal of improving what your knowledge base is, right? You're learning data science so that you can get better at doing something that you think is important. So go out and learn, and don't be embarrassed that this is something that you're learning. And I think a super important corollary to that is, if you know something that other people don't know, well, don't be a jerk about it. You didn't always know everything. Like, just try to learn some stuff, right? And try to help others learn things that you didn't know when you have the opportunity to do so. That advice, I think, is the same as pretty much everything, but it can be difficult in the context of data science because sometimes people, you go off and you write your own code and you don't want to share that with other people, and that's just something that you're going to have to start getting over, right? Is in the same way that if you're going to learn how to write, if you're going to learn how to do really anything else, you need to be able to get input from others. You have to be able to put your code out there and learn, and both get input and also ask for advice. Good old Jake the dog, right? Sucking at something is the first step to becoming sort of good. So don't worry if at first things are hard. That's just part of the process. The other thing that I'm going to encourage you when you are learning data science is to think a little bit about how you are going to ask questions and how you're going to ask for help. And this, I think, does relate. This is a little bit more specific than general learning advice. This relates more specifically to code. And if you have broken code, how are you going to get some examples, or how are you going to get some help with this? If you just say, like, my code doesn't work, no one's really going to be able to help you. And if you just post like a small code snippet, often people aren't going to be able to help with that either. But if what you can produce is a short version that says, here I have isolated a real specific problem and I don't understand why this doesn't work, then other people will be able to help you out with that. And most of the time, and this is just sort of true from my experience and others, if somebody asks me, what's wrong with this code, and I can't run it myself, well, then I'm not really going to be able to answer that question, and it's going to be really difficult to even try. But if you create some code, you share that, and I can check and see, well, that doesn't work for me, and here's why, that makes it easier to answer your question. And so I encourage you to adopt that kind of a mindset. There's the last thing that I'm going to touch on. I've sort of talked till now up to how in learning data science you should build up the things that you know, sort of the known knowns, right? How are you going to learn that you know what's going on in ggplot? All right, you gotta know what you know. The other thing that I encourage you to build is the things that you know that you don't know. And the example that I like to give here is, for me, Python. I can't code in Python. I don't really know how it works, but I know that Python exists, and I know that I don't know what it is. And the reason that I think that's important is that if it became critical for me to use that. If it became important that I just had to, for whatever reason, use Python to solve a problem, well, I know that it's out there and I have some amount of confidence that I can learn it if I need to. What you want to avoid are things that you don't know that you don't know. The things that you don't know that you don't know are things that you can't remember and say, oh, I should go and learn that thing so that I can make progress on this problem. If you don't know something and you don't even know that it exists, then it's not a tool that you can sort of remind yourself to go out and learn. And that's, I think, difficult. So I encourage you to do a couple of things in parallel. First is to really build a core knowledge base, and the other is to sort of become more aware of other things that exist out there so that if they become relevant to you, well, then you have access to them and you can use them. One of the ways that I build up, especially my collection of known unknowns, is through Twitter, is just seeing what is the most recent thing that somebody has posted that's like, check out this cool thing. And sometimes I remember exactly what it is later, and sometimes I don't. Sometimes I think like I'm gonna have to dig through tweets from 3 months ago to find out like what was that particular function that solves the exact problem that I have right now. But I think Twitter is often a really good place to build up that collection of what things you know and what things you can practice and what things you can implement yourself. I mentioned that big data is one of the trends that drove the emergence of data science. And I want to comment on that in a little bit more detail in the sense that data has become viewed, especially in the last 10-ish years or so, as a resource in and of itself, meaning that in an old economy, it might have been the case that oil was a critical resource, but Google isn't an oil company, right? Facebook isn't an oil company. The resource that Google has, in addition to, money and a lot of people and all this other stuff, the thing that often drives Google's success is the data that they have access to, that the troves of information give them some better resource for training new algorithms, for understanding the impact of this ad placement on this outcome, on seeing who's going to click on what. And similarly for things like Facebook and Amazon, right? Amazon is as successful as it is, not just because it's got, a website that everybody knows, but that they understand who is clicking on what and when, and what do they click on next, and what can they suggest, and how can they advertise in a way that's effective. The data is the thing that allows them to do that, and so data in and of itself is a valuable resource. There's a couple of things that, the comparison to oil came up quite a few times. One of the things that is a little bit more recent than some of those other articles is the following. Streaming videos will soon look like bad old days of TV, and the thing that I want to draw attention to is the goal of Disney Plus, which isn't a new revenue line, but it's so that Disney can learn more and more about individuals, that having access to data is, whether or not Disney makes any money off of Disney Plus, that data is something that they recognize as profitable in and of themselves. And I think that quote is useful for sort of contextualizing just how important data is in both our current economy and sort of in society at large. And I also like, not gold and not oil, but the new uranium as something that is useful but can be radioactive and potentially dangerous. And that's something that I encourage you to just sort of think about generally when you're thinking about the data that you have access to and also the data that you put into the world. I'm also going to turn or revisit the question about artificial intelligence and deep learning. It is often thought for people who are a little bit on the outside of data science that AI and deep learning are going to solve all of the problems that they might have in a data set. That what we might want to be able to do is, well, we've got a bunch of data and we don't really have to worry about anything because we can just put an AI on it and it's going to spit out whatever accurate predictions we want to have. There are a couple of really important caveats to this though, and the first is that AI and deep learning often only work when you have really big training data sets, and they are also focused on optimizing very specific criterion, right? So I've mentioned Google a couple of times. You could think of something like YouTube. YouTube has an awful lot of data, and they can train their algorithm for suggesting videos so that the next video that is suggested to you is the one that is going to keep you engaged. They have a lot of information on how to build that recommendation system, and it's probably based on something that looks like deep learning or AI, but it's also focused very narrowly on what is the thing that YouTube can do to keep you clicking on the next video. And that, I think is important to know that is one of the things that these companies are going to be focused on is optimizing a very specific criterion. It's also true that most of the time in the context of AI and deep learning, it's really difficult to interpret the results, and that is a result of how these algorithms get trained. And so this is, speaking of YouTube, I encourage you to watch this video on YouTube, How Machines Learn. The idea is that if you start from a collection of very simple decision makers, things that take some input and make some prediction on the outcome, then you can test whether or not they are doing something correctly. And in this example, they're trying to distinguish images, whether it's an image of a bee or an image of the number 3, or neither of those two things. And so you sort of train things, you get something that makes guesses, and then you see whether or not they're accurate, and you build an awful lot of these things, and you start combining the ones that are successful and then recombining those, and getting rid of the ones that don't work at all, until you're left with, in the end, some algorithm that takes inputs and produces outputs, and those outputs are often very good. It can very accurately distinguish between two different kinds of images, but it can't really explain to you how that happened, and you, even though you've built this algorithm, can't really explain how that happened either. And that, in a very, very broad overview, is like what AI is intended to do, and also some of the limitations of using AI in the context of data sets where you really care about what the interpretation is. To be a little bit more concrete about this than YouTube recommendation systems, I'm going to remind folks about the switch that Google made a few years ago from a old way of doing translation to a newer way of doing translation. The old way is more complicated than this, but was roughly speaking, if I see these words in this language, let me do a dictionary lookup and check some grammar rules and then translate them into these words. And that's the old way. What Google did alternatively in a few years ago was to take written text in this language and human translations of that text in another language, and then as many of those connections of pieces of text as they could find, connect them and just train an AI algorithm to do that translation automatically, cutting out the need for either an explicit dictionary that encodes what words translate to what, or some rules about grammar. All of that was sort of put to the side, and instead an algorithm was trained, an AI was trained to do that translation instead. And the downside to this were things like artificial intelligence can acquire bias against race and gender. Google Translate pairs he with hardworking and she with lazy, among other examples. Folks were able to create these Google translation poems. He is a soldier, she is a teacher, he is a doctor, she is a nurse, where the he and she were automatically generated by the algorithm, not by the person who was writing the poem in the first place. And the issue here was that in this algorithm, or in the training data set, if the people who are translating data from this language, text from this language to this language, if those people or the languages that they are translating from, the text itself has encoded some biases, well, the algorithm isn't going to do anything about that. It will pick up those, and you're not really going to be able to see it because you're not making a decision about what gets translated to what. It's just sort of learning from the text. And so I think that, to me, is one of those things that emphasizes that AI can go wrong and isn't going to sort of be at least a global panacea for everything that we need to worry about. The other thing that I like to mention about AI is that in reality, AI doesn't get used anywhere near as often as people might think it does. And this, when we raise money, it's AI. When we hire, it's machine learning. And when we actually sit down and do work, we're going to do logistic regression. This, I think, is broadly true, that most of the time, things that look like very, very difficult problems involving big data, the best solutions often turn out to be simple things that you can implement and interpret and understand, and that complicated things don't necessarily work all that much better. So I've talked briefly about a couple of the trends, big data and computation or prediction or artificial intelligence. I also want to mention in a little bit more detail what reproducibility is. One of the things that data science emphasizes is reproducibility. And the idea here is that given the same data and the same code, anyone should be able to produce the same results. What that implies is that the code itself is an important means of communication. The code itself is something that somebody else might need to look at, that if you really want to understand what's going on in an analysis, you're going to take a look at that code and use that to effectively communicate what has happened. In later videos, we're going to talk about this in a little bit more detail and see some tools that encourage reproducibility, but the concept of reproducibility doesn't depend on whether or not you're using R or Python or something else. The idea is that you should work in a way that 6 months from now, a year from now, somebody can come in and say, how exactly did you get this figure? And you dust off your code and your data and you rerun your analysis pipeline, and you or they are able to reproduce the same figures and results. The other implication of this, of an interest in reproducibility, is an interest in transparency and openness around code. That if somebody asks you for code, you should be able to say, yeah, no problem, I'm happy to send it to you, right? That openness, I think, is valuable both for your own workflow and for identifying errors, for making sure that the things that we produce as researchers, as scientists, are fair and accurate. Is if somebody sends you some code and they identify an error, that's fine, fix it and move on, right? And that I think of as a completely reasonable way to think about sharing code. And I guess, you know, not to be melodramatic about it, but I think of sharing code as something that you do when you are both confident in your ability to implement things, you are confident in what you have done, but you are also humble and recognize that you can make mistakes, and when you do, that's going to be fine, right? That if you make a mistake, that is not going to shake the confidence that you have in yourself as a data scientist. It's going to be something that's unfortunate, and then you fix it and you move on and everybody's happy, and you continue on with your life, and that's fine. I, in my personal experience, have found that a lack of transparency is usually problematic. It's not any one thing that leads folks to not be transparent. I don't think that's true. There are a lot of reasons that people aren't transparent. The ones that I worry about the most is a sense that the person who has authored some code and does not want to share it believes that they are unable of making mistakes, that they're simply incapable of getting anything wrong. And that, everybody makes mistakes. And that sense that they shouldn't share code because to question them is just unreasonable is, I think, a dangerous viewpoint for somebody who's working in data science to have. Now, reproducibility is important, sharing is important, all of this is important, and like I said, this isn't platform specific, but there are tools that will encourage you to do things in a way that makes you less likely to make mistakes, and that will encourage you to do things in a reproducible way. So I like this graphic for two reasons. One, because that's Hadley Wickham, the author of a lot of things in the tidyverse, which are tools later videos are going to look at, and also because in this example, or in this image, behind him is a slide that he's presented in a couple of different cases, which talks about the pit of success. And to paraphrase, the idea is that rather than success being something that you have to struggle up a hill for, success in the context of using correct tools and clarity and reproducibility, ideally the tools that you are using are going to encourage you to be successful all on their own. That if you simply by using the tools that you have chosen to use, you are going to fall down into a pit of success, well then those are good tools that you ought to use. And those are going to be things that we talk about in the context of this class, but that overall principle of making success a thing that happens inadvertently without any extra work is something that I think is really important. Now, I've mentioned a few times that this is a course on data science, but it's also very much a course on data science in the context of public health. I'm a biostatistician, a public health data scientist, depending on what branding works better at a particular time. Probably both biostatistician and public health practitioner and public health data scientist. All of those things I think are relevant. And I want to talk for a couple of minutes about what public health brings to data science. And in the first of those is what questions folks in public health might choose to ask of data, that it's unlikely that public health data scientists are going to be particularly interested in improving click rates on advertisements or developing a recommendation system that keeps people locked into YouTube, right? Like that's just not questions that public health is particularly interested in. On the other hand, what we might ask as public health practitioners are what kinds of ways can we use data to improve health? Is it possible to use big data or new data sources to improve disease surveillance, to understand who is transmitting a disease to who and in what time and in what mechanism? Are there ways that we can use that to improve prevention efforts, to stop the spread of something, or to prevent the bad, the kinds of health behaviors that lead to bad health outcomes, right? Are there things that we can do to improve the ability to prevent disease and death? Can we understand mechanisms better? And by mechanisms, I mean the things that underlie how a disease or a death evolves. What happens over time? What is it about air pollution that leads to cardiac events in the summertime? What is the mechanism here that we can understand, or we should try to understand better? And are there ways that we can target outreach in a way that's more effective? Is there some way, similar to a prevention effort, is there some amount of targeting that we can do to improve the reach of public health intervention strategies? And I've said this a few times, doing something simple is often more useful than trying to do the most complicated thing. Focus on how it's possible to use data in a way that improves health. That is sort of a public health lens on working with data, but I also want to talk about public health data science specifically. And the sort of reason I like thinking about this is that many of the things that are critical for doing data science effectively are things that public health has been worried about for an awful long time. And some of those, not an exclusive listing, but some of those are things like, who is included in my study? How did I identify this population? And what does that mean for what I am able to learn? Who is represented and who isn't? And what can I learn as a result of that? Given the information that I have, what are the variables that are going to tell me something about association? What are the variables that are going to tell me something about causation? What are the variables that are going to distract from those, that are going to be confounders that I need to be worried about? Because if I don't deal with that, I'm going to learn something inadvertently, something mistaken. Can I talk about what things are important in the sense that they actually have a measurable impact on some outcome? What is it? You know, is there a difference between statistical significance and actual public health relevance? And then in sitting on top of all of these are the general ethical considerations that public health practitioners often bring. Are these the right things to be doing? Are the people whose data I am studying, have they consented to provide those data? Are the algorithms that I'm implementing likely to have adverse events, adverse outcomes for the populations that I care about? And so I think a lot of those points are things that public health practitioners have spent an awful lot of time thinking about, and the addition of some public health, some data science tools to that more traditional public health repertoire really, I think, is a recipe for success. I like this figure also because it drives home some of the things that public health practitioners think about and should be thinking about, and that I encourage you to keep in mind, which is on the left-hand side, obtaining data that gives you some measure of something requires a variety of choices. If you want to measure something like intelligence, well, you have to identify what is intelligence and how am I going to measure that and who is going to reply. And once I've gotten a collection of responses, how can I use that to connect something that looks like the actual edited version of the data that I'm interested in, right? So you have to go through a process of measurement and understand the choices, the assumptions and choices that you're making at each stage. And on the other side, who do you want to get this measurement for? Out there in the world, who am I actually able to draw a sample from? Who actually ends up in my sample? who doesn't respond and why might not they respond, and what does that mean for the ultimate association that I'm going to uncover. So again, this sort of two threads of measuring, on the one hand, what data I'm able to collect, and on the other hand, who ends up in my data set. Both of those are threads that end up being very important in the context of public health, and they are increasingly important, recognized as important in a broader sense in the context of data science. And so all of that, I think, is really important as you're thinking about how to grow as a public health data scientist and as a public health practitioner. And with that, I'm going to go ahead and end this video. Thank you very much.